equilibrium diagram. And I have to mention that the reason why we are interested in the defect equilibria of the material is that, see, in a battery system, the electrolyte has to be ionic conductor. It should not be in the region of the electronic conduction. In other words, when we discuss about the DED, defect equilibrium diagram, we have noticed that a material, depending on the operation parameters, okay, we can distinguish the regions for the ionic conduction and electronic conduction. Something like, there's that. And from here to here, of course, the KD is larger than the KI. Okay, we have ionic conductor in this operation, in this environment. Other than that, here and here is N-type and P-type, okay, electronic conduction region. So in a battery system, the electrolyte has to be in here. We have to operate the batteries in this environment, in these conditions. Otherwise, the cathode and anode and the electrolyte, the electrons has to be transferred in the outer circuit, not this inner circuit, right? So this material has to be in this ionic conduction regime all the time. So we want to know when the material is going to be the ionic conductor. And it depends on the environments. That's why we are interested in a defect equilibrium diagram, first of all. Okay. Let me just discuss about the defect concentration and conductivity. Okay. Conductivity total is going to be a summation of conducting species. Okay. And here, the conductivity of a specific species I is going to be the concentration of the defects and a charge number of each defect has, and electric elementary charge, which is Q is 1.602 times 10 to the minus 19 coulombs. Per charge. Okay. And we have to multiply this thing, the whole thing, with the mobilities. And UI is mobility of that species. Well, we should say it's electrical. There are many different kinds of mobility, but in this case, obviously, it is electrical mobility. And that is the velocity divided by electric field. Okay? And the velocity has a unit of a centimeter per sec. And the electric field is a volts per centimeter. So the mobility has a unit of centimeter square volt sec. Okay. What is the mobility of electron in the silicon? 1420. Okay. Like that, the mobility is a material properties. Material property. This is material property. The reason why we invent this term mobility is that when you want to say how fast the electron can move in the silicon, obviously the speed or velocity has to be dependent on the electric field that we apply to the silicon. So we cannot generally say this velocity of electrons in the silicon. But if you normalize that the velocity with the electric field, then we have a material constant like mobilities. So that's why we has to set up the term mobility, and that is the velocity and electric field. And this slope is going to be the mobilities. Okay. We can see several of this in material science, like the flux and the concentration gradient, and we have a straight line, and that is the diffusion coefficient. Okay, that is the Fick's first law. And also, if you have the force and acceleration, and we have a straight line, and that is the mass. Okay, that is a Newtonian. Now, this kind of thing is a very great invention, as a matter of fact, and this is very useful. For example, if you want to measure the mass of electrons, which is very, very, very light, there is no way, no means to measure that light mass, right? Now, how do you measure the electron mass? All you have to do is measure this force that the electron can feel and the acceleration that we apply. Then you are going to have a straight line. That is the nature. And that slope is corresponding to the mass. That's how we determine the mass of electrons, which is unmeasurable. Anyway, so that is the mobility. So conductivity is going to be defined in this fashion, okay? Now let's think about the unit of conductivity. Everybody knows about the unit of the conductivity, but let's just think about the unit of the conductivity in terms of this equation. Okay, the concentration, that is a particle per centimeter cube. That is the concentration. And the charge is the charges per particle. That is the Z in there. And then the charges, that is the coulombs per charge. That is the Q there. And the mobility here, as we have discussed, centimeter square per volt sec. Okay? And the particle, the charges, then this end up with the coulombs per centimeter volt sec. Okay? Now the voltage is nothing but ampere and ohm. Okay, that's Ohm's law. Here we can have another one, the volt and the current. Then we have a straight line, and that is the resistivity. Okay. And that is coulombs per second. That is ampere and ohm. So the conductivity unit now becomes coulombs per centimeter sec times sec ohm coulombs end up with the 1 over ohm centimeter. So the conductivity has a unit, something like this. Okay. Let me just review some of the discussions that we have about the DD. Okay. When we have situation that the Ki is greater than the Kd, then we have equilibrium DD like this. That is the slope half. Half here, and then the slope 1 here, and then half again. And this is the 2 lines. Okay? That is if here Ki is greater than the Kd, here the major defect is going to be electrons and holes, okay, which is about the same concentration. But if you have situation that Kd is greater than the Ki, then every time we have this kind of figures for the DED, but in this case, the ionic defect, the positive defect is going to be equal to the negative defect. And in this diagram, the conductivity, if you plot the conductivity and same parameter log F, it's simple, right? You have all the electronic conductions like electron and the hole conductions, conductivity corresponding to the electronic holes, like this fashion. And then this is the N-type we call, this is the P-type, okay? Something like this. Now, if we have this situation, then we going to have something like this that you have seen before, conductivity and log F. And only at this part is going to be ionic conduction. And this part is going to be N-type, and this part is going to be the P-type. So a material can change its type depending on the environment. And we can add one more thing for this defect equilibrium diagram, which is if we plot log delta m t, okay, the stoichiometry thing and the log f, then we're going to have curves something like this. Very narrow, thing like here. And remember the delta, the non-stoichiometric parameter, delta m t is equal to b Vm minus a Vx naught. In case of a Seung-ki disorder, okay? And it's going to be equal to minus b m minus Vm prime if it is the Frankel. The dominant defect is the Frankel disorder. Okay, and virtually, practically, this is a delta minimum. Okay, and this part, this is a negative delta, and this is a positive delta values. For this whole discussion here, so in practice, the delta minimum can be thought as kd, square root of kd over m total for ki is greater than kd case, and it can be said ki square root of ki mt for kd, ki is less than kd case, the ionic material and electrical materials. Okay. Let's see if we have a phase diagram of the material, and if the phase diagram is going to look like this. Okay. Of course, this is temperature, and this is element in A and B. Let's just think of this the phase diagram. If some material is any material have this kind of a phase diagram, then we know we have two-phase region like this, and of course this is a liquid. Okay. And we are working on this sample at this temperature, this particular temperature. Then if you draw the activity, corresponding to that A and B element, you can think in a pure A, you add the B element, or you can start with the pure B and you add the A element. And then you just changing the directions. And if you want to plot the activity of B, for example, when it's a pure, then the activity is going to be 1 here, and here the activity of B is going to be 0, right? And then you have, in between, you have alpha phase as a single phase, and beta phase in the middle, and the gamma phase at this far end here. And in between, we have two-phase region, and in this two-phase region, the activity, we do not have any gives freedom, so that this is invariant. In other words, we do not have any variables here. So the activity of B should be constant, okay? And all you have to do is just to make a connection of this. And this is how the activity of B is changing in this material as we move from pure B and add A, something like that, okay? And this is beta plus gamma. Actually, this is very important to notice. See, for example, from here to here, okay, this is the region where the beta phase is stable. In other words, if you add more A or B, if you move these directions, you just put more A to this material, then you begin to saturate, you begin to precipitate, you begin to form a alpha phase in this pure beta materials. Then you can begin to see the alpha phase, something like that. And then as you move towards this directions, this alpha phase becomes fat. You know. So, but if you move these directions, then you begin to form a gamma phase in this case. So you have to stay here if you want to have a pure beta phase. It just says that. So you're not going to move anywhere less than B here, and more than B1 or less than B2 if you want to make your material stable to have a beta phase, okay? So this is a very important, and if you think, we're going to get into this shortly, but if you think about the battery system, okay, if your cathode material is, say, it has a certain voltage, your battery is working at 3 volts, okay, then it means that you're working on this plateau, or you have to work on this plateau, because the concentration or activity of B is directly related to the potential, the voltage that the battery can have, right? So if you want to have a battery like 3 volts, stable, then your material has to be in this region or in this region, this plateau regions. If your material is in a single phase region somehow, then it means that by changing the amount of a B or A in your material, then the voltage is going to change following this curve. So your voltage, your material is not the 3 volts anymore. Okay? So identification of the stable range is always very important in a development of the cathode material. Okay? Defect equilibrium diagram is very important for the electrolyte because the electrolyte has to be ionic conductor, right? This phase diagram and the related activities is very important for the development of the cathode material. Okay? Now let me give you some of the examples. Now, general case of oxide. Now, if you have a pure M and M2O and MO, M3O4 and M2O3 and MO2, okay? As you increase the oxygen partial pressure, which is equilibrated with the metal M, okay? Then you're going to have this kind of a phase change. It can have phase changes. And here you have a alpha phase, beta phase, gamma phase, and delta phase, and in between you have a two-phase regions all the way, okay? But one tricky thing here, is that this kind of information can be seen in the Ellingham diagrams, actually. Let's say you have alpha phase and M plus MO, two phase, and an MO phase, and MO plus MO2 phase, and MO2 phase, things like that, okay? Let's suppose you have this. This is the oxygen. There is, as a matter of fact, what we can have in the Fe system. We have exactly something like that with the Fe system, oxidation of oxygen, ion. And if you have some situation like this, then of course you're going to have a corresponding activity curves. Something like this is a something like this. Okay, here. You're going to have some activity curve, something like this. That is actually log PO2, partial pressure of oxygen. That is corresponding to the activities that we have been talking about. And this is X in MOX. And it's kind of a titration curve. Titration curve. Okay, we're going to titration curve later for the actual system. Now, what I'm trying to say is, in practice, MO is going to react with MO2 to form MO2. MO is going to react with the oxygen to form MO2. This is what really happens in practice. But if you want to know the Gibbs-free energy for the formation of MO2, in the Allingham diagram, you just have these reactions. So that the delta GF0 for MO2 is always higher than the actual gives phase gives energy for the formation, because see this for this MO2 formation, this happens always first, and then with that we are going to have a reaction like MO2. So as a total, you're going to have this reactions, okay? But in the Allingham diagrams, the Gibbs formation energy is just directly calculated from this reaction, so that this much is going to be, this much has been added to the actual formation energies. Okay, that's the one thing that we have to careful and read the activity and the reaction thing. Okay? And let me give you some of the discussions related to the influence of temperature on the conductivity. Okay. If you look at the DED diagram carefully, then what you can see is, if you set this is the log F now, the y-axis is the log F, and then this is the temperature, 1/T, then you may have the regions distinguished into three types, N-type and P-type, and this is the ionic conduction range. So that if you working on your material at this temperature, then you are going to have ionic conductivity with this much freedom of the operation conditions. Okay? But if you put your material at this high temperature, then you never have that ionic conductivity regions. Okay, things like that. And also, we have seen that the reaction constant is related to the free energy changes, something like that, so that the K is going to be the exponential over RT, and then that is the Arrhenius type plot, log K and 1/T. Then we're going to have a straight line, and this straight line is related to the delta G of R, where we usually call this in the Boltzmann term, that is the activation energy of the reaction, right? This kind of thing happens only when KD is greater than KI. Okay, but in most of the cases, Ki is greater than Kd. In most of the cases, Ki is related to the band gap of the materials, and then Kd is the ionization of the defects. And the ionization of the defect is usually difficult, and it requires a higher activation energy than the electron hole formation in the materials, in the semiconductors and so forth. We usually have a situation that Kd is Ki is always greater than the Kd. Okay. So in most of the cases where we have Ki is greater than the Kd, the defect, the equilibrium reaction constant 1/T time temperature dependence is going to be something like this is ionic and this is electronic. And if we have large band gap material, then this log K versus 1/T is going to be, this is going to be electronic. And this now is going to be ionic. Okay. So in this case, we have ionic materials at the very low temperatures, but it's not that practical. Okay, that is about the defect equilibrium diagrams, and we just have reviewed of it. We just extend the idea of a defect equilibrium diagram to the non-stoichiometry and the temperature dependence and the conductivity thing. Okay. Next time we want to discuss about the effect of a third element in the binary system. We have a MX system, and what happens, we're going to see what happens if we add some third element like a C in the binary MX system. In a semiconductor, it is going to be called doping, right? But in ionic materials, it is not usually called doping. But we just to see the effect of a third element on the binary system MX on the Wednesday. Okay? I'll see you on Wednesday then.